I've written a list of fractions up here. What you're told to do is start with the number 2, and then from now on you multiply the number you have by the first of these fractions that gives a whole number answer.
So you have to go a long way.
Which in this case is m, and so you'll get 15, which I'm going to write as 3 times 5. And now, so the only possibilities are those whose denominator divides 15. And if you look along, there are none of those.
55.
Oh yes, there is. There's 55. And so we'll, by the way, we used, which did we use? 15 over 2. We used m. And now we'll use n and get 3 times 5 squared times 11. And now we can use e because there's usually a big prime in here, where big means 10 or more. The big 91 isn't prime, it's 7 times 13, so the big prime is 13, and that's not 11. The big prime is 17, the big prime is 17 again, the big prime is not, the big prime is 11 here. So I'll use e, and I'll get, that'll rub out the 3 and the 11, and replace them by a 29. And then the next one was the first number for which the denominator, f. So we'll use f, and so on. That's the game. It's not a very interesting game to play. So what you're told to do in this game, which I call prime game, is look out for the powers of 2. And, well, we've had one at the beginning. Let's not count that. Eventually we find 2 squared. I'm going to write in red here the stage, 0, 1, 2, 3. By the time we get to 19, we find 2 squared. It's a power of 2. So we take a photograph of it with our brownie box camera or something, because we probably want to show it to our grandchildren. And then at stage 69, there's another power of 2, 2 cubed. That happens at stage 69. And then at stage 200 and something, we missed 2 to the 4th. I wonder why. We get 2 to the 5. And then rather later, we get 2 to the 7th. And most mathematical readers will guess what the sequence 2, 3, 5, 7 is. Especially, however, I gave the game away a little bit before. This is a computer program for computing primes. You see 2 to the nth if and only if n is prime. And I got interested in this a long time ago. It's part of a sort of continuing interest in ways of calculating things. I'm not terribly interested in doing it efficiently. I'm not a very practical person. I like theorizing about it. And it's an interesting remark that any computable function of integers, taking integer values, can be computed in this sort of way by a list of fractions. I wrote down once in my little paper on this subject a particular list of fractions that if you feed it with 2 to the n, the next power 2 you'll see is 2 to the nth decimal digit of pi.
Oh, so you start with 2 to the n instead of 2?
Yeah, if you start with 2 to the 0, you'll get the 0th decimal digit, which is the one before the decimal point, namely 3. 2 to the 1 gives you 2 to the 1 again. 2 to the 2 gives you 2 to the 4th, because the second decimal digit of pi is a 4. And it goes on 3.141592653589793238462, etc. And it always gives the digits of pi. However, it's a very, very slow program. In fact, if you fed it with 2 squared and waited, then I think you'd be waiting until after the universe finished before it would compute it. But theoretically, it computes digits of pi.
And any possible program can be written in this language.
Yeah, essentially. Any program, any computable function from integers, from non-negative integers to other ones, can be computed by just a list of fractions like this. I wrote a little paper called Unpredictable Iterations about that. So, you may have heard of this 3n+1 problem. Do you know it?
Yes.
This is a nice little sort of game you can play. Well, it's a nerdy sort of game. You take a number. If it's even, you halve it. If it's odd, you multiply by 3 and add 1. And the conjecture is, it's due to a man called Lothar Kollátz, German, who dreamt it up around 1940, I think. The conjecture is that this always ends in a 1. And it's pretty clear that it does, but I don't expect anybody to be able to prove that. It's been verified for numbers less than 1 billion. Something like that, anyway. Yeah. That was one of my recurring sort of themes. The simplicity of ways of calculating things. You know, I read the standard sort of books about great discoveries in mathematics when I was a student, and Gödel's theorem is this very famous theorem that a formal system for proving things about arithmetic necessarily can't prove everything that's true unless it also proves some things that are false, and so on. And Gödel proved this theorem using Gödel numbers, which are ways of numbering essentially computer programs. And the books always used to say, of course, the Gödel number for any statement that's interesting will be enormously large. And I sort of didn't see why it had to be. Or, various things like that. And so this list of fractions
Could be a number.
it could be, it could be coded up into an integer, and it wouldn't be all that large. And, that one computes primes. So I was interested in simple ways of computing things. And that led me, at a different time, to my interest in this life game.